All right, can everyone see the brief intro to matplotlib? All right, cool. All right, so this is a crash course meant to summarize and complement the official matplotlib documentation, which is on the whole excellent. And I encourage you to refer to the original documentation for fuller explanations of function arguments and also to help you with the exercises. Anyway, I think you're all using Python 3.x at some point, or by now, probably 3.11 something, or maybe 3.10 to 3.12. You need NumPy. It helps to have experience with SciPy and pandas, and if you intend to use matplotlib to produce publication quality plots, you will also want to, it would also help you to understand a bit about LaTeX math typesetting. And as a more general knowledge, you should also be familiar with the terms args and quargs, because they will you'll see them a lot in the official documentation, and you'll see a bit of them in this presentation on matplotlib. So args refer to positional arguments, and they're usually required. They always come before the quargs, and the quargs are short for keyword arguments, which are usually optional, but a lot of times it's fairly common to see functions where you have to give at least one of a certain number of quargs, dependent on other inputs. Anyway, so how do you run? Depends on your cluster. The main thing to remember is that in most places you will have to find a load of matplotlib, and that will depend on a previous Python version. In most cases, you'll also need to load in some cases, you'll need to load a tk-enter module in order to display the plots. But generally, it's enough to import Python and then matplotlib. So HPC2N, you'll have to preload HPC2N. You'll have to preload any matplotlib and any other prerequisites if you want. Okay, sorry. So these are the available versions that are on HPC2N. The recommended version right now is 3.8.2. Just use the one that doesn't end with an E. And on LUNARC, you'll need to preload a particular version of Python, which you find out that's which one is appropriate by just doing for instance, let's say I want to load Python 3. Let's say I'm working with Python 3.11.5. So I need to know what modules are loaded with that. Well, first I have to load this GCC core module in order to make that available, then load Python 3.11.5. What the heck? Oh, ML. Okay, and then that will determine which matplotlib gets loaded if I just do that. Oh, it may have another dependency. So let me do ML spider matplotlib. So what else does this depend on? I'm going to use 3.8.2 because last time I checked, there was a bug with 3.9.2. So ML spider 3.8.2. It needs the full GCC, not just GCC core. This is why I usually load just GCC instead of GCC core. Okay, so I've got these modules loaded, and now if I type matplotlib, matplotlib, once I've set other prerequisite versions, as long as that determines exactly one version of matplotlib, you don't need to specify the version anymore. So that pulls in a ton of modules, and that loaded matplotlib 3.8.2. Now I showed this mainly just to show the module dependencies, but you don't typically have to worry about this if you're going through one of these on-demand applications, because everything will be loaded for you. For instance, if you're using if you use both Jupyter Lab and Spider depend on Anaconda 3, and those preload Python 3, SciPy bundle, which includes NumPy, Matplotlib, Pandas, all of those different functions. So I'm going to close this. UPPMAX, you've got these different. The matplotlib is part of what matplotlib depends on these packages, and then you can load these versions of matplotlib, which look a bit old. In NSC Tetralith, you've got these options. There's only a couple, and you'll need to load not just GCC, but also this build tool -easy build /4 stuff. And you can see that if you just type in module spider matplotlib and then the version number. Again, you'll need to use tk-enter to show the images. And on PDC Dartle, due to the limited number of ThinLink licenses, it's assumed that you'll be using SSH with X forwarding. Matplotlib also, like most modules on PDC, this requires you to load a PDC version. So in this case, PDC 23.12. And then you can load matplotlib, and you'll need to use this longer version here. I never have found exactly what this short version is an extension of. But in order to use most of the other Python functions related to this, you'll also need to preload one of these cray-pythons 3.11 point something. And those include NumPy, SciPy, MPI, 4Py, and all that stuff. So it's only matplotlib that depends on this PDC. And in most cases, you'll want, after importing, so in all cases, once you've got the modules loaded and you've started your choice of IDE, the very first thing you'll do if you want to use matplotlib is type from matplotlib, import pyplot as plot. That's the main plotting module that's part of matplotlib. In a lot of cases, you'll also want to import matplotlib at the top level. So like import matplotlib as NPL. That's what I usually do. And that's important if you have to specify something like the display backend, which you will have to do most of the time. So I think I have it down here. Yeah. So once you've imported matplotlib, usually for most of these, unless you're on the Cosmos on-demand apps for like Spider or Jupyter, or if you're in Jupyter Lab on another machine, most of the time you'll need to include in your code this matplotlib.use and then tkag. That chooses an interactive display display medium so that it will actually show your plots when you type plot.show later on. We'll get to that. I see a question in the chat. Oh, no, sorry, that's a QA document. Okay. So what do you do once you're in? At the regular terminal, matplotlib figures typically do not display. Okay, so now we're talking about the, this is a little bit more detail about the back end. Matplotlib figures typically don't display at the command line unless you set the back end that allows displays that is compatible with your version. Except for Rackham, which should run without you having to set a backend. So the backends are engines for either displaying figures or writing to image files. For the command line, for any Python code, plotting code that you want to run at the command line, and for Python versions 3.11 point something, you typically want to use a tk-enter based backend. Sometimes you'll have to load tk-enter separately. Most of the time you don't. Most of the time it's pulled, depending on your machine, it's typically pulled in by loading the matplotlib module. But again, you typically will have to import the top level matplotlib package and then run matplotlib.use tkag before you do any plotting. If for some reason that doesn't work, or if you're on Rackham and the default backend doesn't work for you, you could try matplotlib.use qt5ag, but you have to make sure that you first imported qt5 and pyqt5. And these things are not needed in Jupyter or Spider. In Jupyter, what you do is that once you've imported pyplot and any other submodules you need, you would add this %sign matplotlib inline before making any plots. You do not use matplotlib.use. And in Spider, it kind of depends on the version, but the default is for the figures to be displayed inline at the Python console or in a graphics tab that's in the upper right. These are usually too small. So I'll show you what I've done in Spider to make it pop out a GUI that's easier to resize and interact with. So let me quickly start a Spider session. And so then let me see if I can't. Okay, I'll have to get back to the question on the Intel modules. In all likelihood, it has something to do with which tool chains you're using. Because a lot of these depend on a free and open source tool chain, and Intel is proprietary. Okay, so in Spider, if you want to, let me see if I can't zoom this in a bit. View.
Probably Control plus or Command plus usually.
Good. Thank you. But that doesn't really help with the menu options, unfortunately. So if you want to set it so that your plots pop out in a separate window that you can resize and interact with, what you want to do is go under Tools, then go to Preferences with this little wrench icon. And then you go to IPython console, click the Graphics tab, and the default option is typically inline, and then you change that to automatic. Here you can also fiddle with the default sizes and resolutions. I am going to bump this up to 150. Apply, say OK. And now, if I run this file, which already has a bunch of plots in it, got this figure here that pops out in a separate window. And now I can click these options here and adjust the borders, spacing between plots, or I can even go to these. I can even go to this axis window and adjust, say, the markers or the limits. For sometimes, if you have multiple curves on the same plot, you can also adjust the Sometimes it will let you adjust the markers, the type of marker and the color and things like that. So anyway, going to shut that off and go back here. So matplotlib uses a default resolution of 100 dpi, as you saw, and a default figure size of 6.4 by 4.8 inches, or about 16 by 12 centimeters, with the default backend. But you can change that, as I showed. With Jupyter, the resolution by default is 80 dpi, which you'll typically have to bump up, particularly if you're making figures for publication. So if you're producing a plot, there's a plot.figure and plot.subplots that you'll need to, that I'll talk about in a few minutes. And those let you change the figure resolution at runtime with the DPI quark. You can also adjust the figure size and aspect ratio with this fig size quark, again in plot.figure and plot.subplots. But you'll have to sort of mentally convert to inches or do the calculation. So I want everybody to start by, as a challenge, I want everybody to get their plots, get their choice of IDE up and running, so development environment up and running, and get matplotlib loaded. Any other difficulties or questions before we move on? Okay. So now let's get to the introduction to the different terms and the application programming interface for matplotlib. So you've already seen me talk about like plot.figure, the pyplot function. So that's what you, that's pretty much the first thing you make anytime you're going to make a plot, is a figure instance. And that in the figure is everything that is included in the in a graphics window. So it's the canvas, it's the plot itself, it's everything. It's the canvas and everything on it, basically. Most figures will have one or more sets of axes instances, and those are the grids and the frames that the plots live in. So everything that's bounded by this black outline here is an axis instance, and so are the these little tick marks, the little dashes sticking off to the side, the labels for them, and the titles of the axes. Those are all considered part of the axes instance. Each individual axis is also its own object, and you can call those to turn on things like grids or ticks or adjust like axis scales, things like that. And it won't come up very much, but you'll also, you might occasionally see something, the term artist. And in Python, almost everything is an object, and in matplotlib, the figure and everything on it are objects, and every object is an artist. So that's every axis, every data set, every annotation, every polygon, every legend. The word typically comes up in the context of things like drawing, like manually drawing plot elements like polygons or color bars. So you won't often have to worry about it, but be aware that it's there because it will come up if you have to draw shapes on your plot. So those are the basic terms. So now, if you look at some common demo codes, one of the things you'll often see is a expression that looks like fig ax equals plot.subplots, for instance. So what are fig and ax? Well, to explain that, you have to know that there are two choices of application programming interface. So there's the implicit API. That's the one that is sort of like the one that most people do as my first plot. It's a quick and dirty way to visualize isolated data sets if you don't need to fiddle with the formatting. Then there's the explicit API, and that's the method that gives you handles to the figure and axis objects. So that's the way you want to work if you need everything assigned to variables so that you can call functions off of them and make adjustments. It's also the API that you want to use if you're going to be plotting multiple plots on one figure. So let me show you a demo of each. Most people's first attempt to plot something will look like this. You'll import NumPy to produce the data. You'll import matplotlib.pyplot as plot. If you're in Jupyter, you would use this %matplotlib inline. And the reason I'm using this here is that this whole code block and its output, the output is produced by a Jupyter engine. So anyway, I've mocked up some data, and then I do plot, the X values, the Y values, and then a string that gives the formatting for the line. And this particular function lets you specify multiple curves as long as you don't have to label them. And then I just do like plot X label, plot Y label, and plot title to give the titles of the different parts. And then I type plot.show, and that produces the output. The explicit API looks more like this. You start with a fig.ax, or figs, ax, and you set that equal to something like plot.subplots. You almost always use this .subplots function, even if you're only plotting a single plot, just because it sort of provides a ready-made way to interact with and iterate through one or more sets of axes. So then once you have this axis object, you then can call the basic plot function off of that. So ax is basically short for pyplot.axis. And then in these cases, the titles, and this also applies to axis scales and things like that. In these cases, if you're calling titling and scaling functions off of the axis object, it will need to have this set underscore in front of it. So it'll be set X label and set Y label and set title, which is not like the implicit interface. But you'll still need to include this regular plot.show because that's a method of plot, not of the axis object. And this produces the same output. And all of these code snippets are, if you hover over the top right corner, you'll see this little these two little overlapping squares and a copy text. So you can just copy these code snippets and run them to experiment with. So as a little, I don't think we'll have time to actually wait for people to complete this exercise, but if you want to be working on this in the background, you can also try to create an array of 50 values from -5 to 5, and then plot y equals 1 over parentheses 1 plus the exponential of -x. And if you do it right, the curve will look something like this. So I'm going to hide that again. So now if you want to plot multiple plots, this is where the fig and axes, the explicit API really shines. So if you do this, then if you do something like fig ax equals plot.subplots and then set in rows or in calls or both equal to a number greater than 1, then axes becomes, or then this axis object will become an iterable. And that means you can index it and loop over it. So then you can, like for instance, if you want to plot on for this example, I plotted 2 plots in one in each row, in 2 rows. And so that gives that makes axes a one-dimensional array of length 2. So we have an axis 0, which is the top one, and an axis 1, which is the bottom one. If there were 2 rows and 2 columns, then axes would be a two-dimensional array, and you would need 2 sets of these square brackets. And the nice thing about doing subplots like this is that you can iterate over them as long as the options are all the same. So in this case, I'm setting both of the axes with the same Y label, so I can just do for ax and axes, ax.legend to make the legend show up, and ax.setLabel. And this holds as long as the commands for both are the same. If I wanted to tune these legends individually, then I couldn't do this with this legend command, for instance. Or if I wanted to set different axes labels, it wouldn't make sense to iterate. But in this case, they're the same. And then, of course, you always have to do plot.show. There's also the plot.subplot singular and fig.addSubplot methods. They require more code to put more than one plot on a single figure. The main use case for them is if you have different projections on each axis. For the subplots, each plot can only be added one at a time, and there can be no more than 9 plots in one figure. But again, this is what you would have to do in order to use different subplot projections. So here's an example where I've done that. So I've instantiated figure and axes separately. So fig equals plot.figure. Here I've set the figure size so that these are not too squashed. I've set one of the axes equal to plot.subplot here. And I've given it a number code where the first is the total number of rows, the second digit is the total number of columns, and the last digit is an index number for the plot. So if you have a 3x3 plot and you're putting the very last plot on you're plotting the very last plot on it, you would have something like 339 or 338, 339. So then for each of these, I've also instantiated a second axis object. And in this case, I've set the projection to polar. And that's why this plot is circular and this one is not. So it takes a little bit more code, but this is handy if you want to do different projections. And I see some more questions. Oh, never mind. They're not questions. They're quotes. So the exercises are in the exercise tarball, and they're also available in the exercises folder if you want to download them singularly.
Yeah, but there's one thing that is they are not on the they are in the top level of the exercises tarball, so in just under exercises.
Okay.
It looks, yeah.
Okay. I've already gone over the numbers here. There is a final alternative if you really want precise control over the the shape and spans of each of these little plots, and that is subplot mosaic. And I've singled it out because even though I haven't seen it very much, it's new, it's new, it's shiny, it's really flexible, and the interface is actually quite nice. So each plot is identified by a single ASCII character, which you repeat for however many over the rows and columns to specify how each plot spans multiple rows and columns if you want that to happen. And then you can use the character, the full stop, to denote gaps. And you can write out these character streams in a very intuitive format. So the plots, so it actually sort of reflects the grid shape of the final plots. So in this one, I have 4 plots in a blank space. The first plot is that I've titled A, spans 2 rows, but only 1 column. Plot B spans 2 columns and 1 row. C spans only a single cell. Then there's a space next to it. And then there's plot D, which spans the entire bottom row, like this. And then this little loop here is just to add this letter label to the center of the plot. And then you can access each of these. The other nice thing about this is that you can then access each axis instance not as an index number, but as by their names, their string labels. And that makes it a bit more foolproof when it comes to figuring out which plot you're putting where. And also you get this very nice per subplot quark that you can give a nested dictionary to. And then you can give, in each case, you can give the keys that label each of your plots as dictionary keys, and then give them a sub-dictionary where you pass quarks that would normally be taken by plot.subplots. Like, for instance, if you want to specify the projection or the axis scale, things like that. And you can assign the same results to multiple plots at the same time by putting the dictionary keys associated with each plot in parentheses, like this. So in this case, both B and D have an x-axis that is log scaled. And I was able to set them both at the same time by giving them as the 2 axes names as keys, and then giving it a colon, and then the quark x scale colon log, and that's the axis scale. So that's a really nice way to handle different different plotting layouts. And then what do you do if you want to save your data? You've got plenty of options. So if you don't want to have to plot the GUI and then save it from the GUI, you can use plot.savefig, give it a file name, and then specify transparency, the resolution, the format, things like that. That's the general purpose function. And the format is where you specify the string type of file. So like PDF or PostScript, PNG, that's the default. You can also use msave if you have an RGBA array image. That's kind of a special case. And alternatively, if you're using an interactive GUI, where have I got it? Spider, like this. So let's say I wanted to save this figure. Well, there's this little floppy icon right here that I can click. I can go to wherever I'm planning to save it, and then say, like, let's say figure 3. If you go through here, you'll notice that SVG is actually available here. Normally, matplotlib doesn't make that available by default, but if the module loads something like Pillow, which is an extended graphics package, then that gives you access to vector formats like SVG, TIFF, and WebP. I'm going to try saving it as an SVG. So it's saved like that. And now if whoops, that's not me. That's in a different window. Now if I go to my files and navigate to my documents and look for the figure, there it is. And I can zoom in on arbitrarily large, and you don't necessarily see the pixels. So that's nice. I'm not going to go into much detail about the standard available plot types. They're all very easily available and visually indexed on the matplotlib official documentation. So if you go to matplotlib, there's this plot types tab that you can quickly navigate to, and then you can see all these different pictures of all these different plot types. And they're handily organized by different types, different subgroups. So you've got the standard pairwise data, statistical distributions, gridded data, irregularly gridded data, which is pretty much just one thing, and then the 3D volumetric data. Okay. Let me very quickly go through the placing of legends and text. There's a base function text that you can use to add text to your plots. You can also add annotations that adds arrows to it. For legends, it's typically enough to just do plot.legend or ax.legend, but if you need to tune it, you can give locations with this lock kwarg, and those can be specified as 2-word strings or digits from 0 to 10. You can also use this bbox to anchor that uses unit axis coordinates, which are the coordinates specified by transform equals ax.transaxes. And what that does is that that lets you place elements, and you specify the placement as a value from 0 to 1 for X and Y if they're within the plot area, or less than 0 or greater than 1 if you want to put the legend outside of the plot area. And there are also whole figure legends that you can use a 3-word string where the first word is outside. Finally, let's talk very briefly about math text. So most journals will expect that you typeset your variables in math scripts so that they appear the same on your plots as they do in the main text. Matplotlib now supports most LaTeX math commands, but you still need to know some of this basic syntax, which is covered in this link. And you may need some extra packages for very obscure symbols, but I don't think that's really needed anymore. LaTeX has been, LaTeX symbols have, most of the LaTeX symbol library is available as of matplotlib 3.7 and above. But there is one very important caveat, and that is that Python and LaTeX both use curly braces for different functions. So that causes a collision that you need to adapt to. If you're using string.format to insert values that you've previously calculated, all the curly braces that are associated with LaTeX commands have to be doubled. And that includes braces that are already nested. So if you have an odd numbered number of nested curly brace pairs, the innermost one will be interpreted as a cite for string insertion. For some symbols, you also need to have this R for raw input in front of the string. So you might, like if you have a really long text string like that, then you'd have to put this R in front of the first quote. And there are also space operators that you can use to insert or remove spaces. And most basic operator symbols can be used as is, but the $, the percentage sign must be preceded by a backslash or double backslash to escape their typical usage. And finally, unfortunately, if you have a really long string like this with LaTeX formatting, you can't really split them over multiple lines because the new line character will still be rendered. So this is an example that shows all of the LaTeX commands needed to insert values and typeset properly in this example here. There's plenty of, I know I'm running over time. This was originally supposed to be an hour-long lecture, but mistakes happen in the scheduling. Anyway, so we've got I've already gone over
The problem, I mean, you can continue to 15:45, right?
Weren't we supposed to take a break for 15 minutes?
Yeah, and then we have a half an hour until the ending.
Yeah, but that half an hour was supposed to be for exercises.
Ah, yes. Okay. Okay.
Anyway, so the documentation on all of these different options for setting axes, axis labels, titles, legends, grids, and axis scales are all pretty good. Just one note about setting the axes X and Y scales. There is if you have to set the axis scaling to a custom function with this function string, then you have to specify both a forward and a reverse transformation. So all of these options do exactly what they say. I had an example here for to show how you can adjust axis ticks and locators if you need really fine control. Usually automatic tick spacing is fine, but you might need to modify the auto-generated tick labels and spacings, or set them entirely by hand if you want any of these things. So units with special formats or symbols like currencies or coordinates. If you want irrational units like multiples of pi, qualitative variables like countries, species, relative size categories, things like that. You can usually specify like if you're doing something like that with a bar plot, that the quark to specify those is usually included. You also might need axis tick labels centered between major ticks, like if you have bins. If you want secondary axes that are transformations of the primary, if you want custom or power law axis scales, or if you want log, symlog, or A sin H scaling with labels on every decade, if the visible major ticks, or if the major ticks span more than 7 decades. So here's an example that shows the rather non-intuitive log locator, where I'm showing two very important quirks, or actually 3 very important quirks that you need to be aware of when it comes to setting the locators. So if you want to set the log locator manually, you specify, so you have to load this matplotlib ticker module, and then you call the y-axis, call set major locator off of it, pass it the ticker dot log locator, give it base 10, and then this num ticks, you don't actually have to know a priori how many ticks you're going to have. You just have to give it more than you expect to appear on the final plot, or at least as many as you expect it to appear on the final plot. So it's helpful to just give it a number that's kind of ridiculous, but not too ridiculous, like 99. And that way you don't have to calculate anything. Then to make sure the minor ticks are visible, then you set minor locator, ticker.log locator, base 10.0, and then there's this subs quarg. And these are not endpoint inclusive. So you only want to include the fractional positions of the ticks between one increment of the major tick. So if I want ticks every 0.2 of a decade, then I have this, I give this subs quarg values of 0.2, 0.4, 0.6, and 0.8. And then I use do the numticks trick again. And lastly, you really want to make sure that when you call set minor formatter and then ticker.null formatter, what this does is that this turns the labels for the minor ticks off. And if you don't do that, your axes will just be a huge mess. You won't be able to read anything because it'll just be a smear of ink. But anyway, you can read through this example in more detail at your leisure, because this includes an example of a secondary axis as well. And finally, there's the placing and formatting of color bars. So color bars, it's worth noting, are methods of figure, not axes. So what you have to do is you have to give it an axis. You have to assign the plot or the axis instance to a variable, pass that as the first argument, and then you have to pass the axis object itself as this ax quarg. And the reason that it allows you to do this is that it allows you to specify the same color bar for multiple images. And you can put that on a separate, you can even put the color bar on a separate axis all to itself. And that's one way that you can resize it to better fit on a grid with multiple subplots. All the other arguments, you can find those at your leisure. So like if you want to imply that the data have been sort of cut off, truncated, or the color map has been truncated, you can use this extend quarg and do min or max or both. And that replaces the squared off end with this little caret symbol. And you can also specify all the same ticks and locator arguments in this format quarg. And that lets you fine tune the formatting and the labels and the axis scales for the color bar. Whew, okay. That was a lot to compress in one lecture. So here are the key points. So matplotlib is the essential Python data visualization package with 40 something different plot types to choose from depending on the shape of your data and the qualities you want to highlight. Almost every plot will start by instantiating the figure and axis objects with this fig, ax equals plot.subplots, and then whatever arguments you want to give it. And most of the plotting and formatting methods are methods of axes objects, but a few, like color bar, are methods of the figure. And some are arguments of both. The exercises and their solutions are provided separately in Jupyter Notebooks. You also need this data file in your working directory. So it'll be exoplanets _ 5250 _ Earth units _ fixed. Okay, thank you. Sorry for running over. There was a scheduling error that this was originally supposed to be an hour lecture and an hour of exercises.